Right. Do you guys have any other questions on estimation theory from the last set of slides that we went through before we get into tracking? Okay, well I told you on Monday that I'm teaching this class upside down, which means as quickly as I could, I wanted to get into the actual tracking algorithms and the sort of core content for this class. And as I also said, particle filters are sort of the highlight of this class. Not to diminish what Dr. Wan will be teaching you later about unsymmetric Kalman filters, but they're the highlight of this class, and these are one step away from them. I wanted to, before we talk about particle filters, I wanted to talk briefly about optimal tracking. As graduate students in a fairly advanced signal processing course, this is stuff you should know. It's not that you're going to use it, but you should be aware of it, and you should know what the ideas are that are conveyed by those. So this set of slides is about doing tracking optimally, which you can't do in practice because these techniques rely on those integrals that we talked about last time. There's integrals that you can't evaluate analytically, and so the only way to implement an optimal tracker is by evaluating those integrals numerically. But it turns out we do have fast computers, and in some cases you can evaluate the integrals numerically. And when you can, this is absolutely the best way to do it. It's optimal, you can't beat it. Its only limitation is really the number of computer cycles that you can throw at it. It rapidly fails in most practical problems of moderate to high dimension, but in really low dimensional problems this works beautifully, and it provides a lot of intuition and insight as to what we're actually trying to estimate. Everything else that we're going to be talking about is trying to do this, but it's not able to actually do it. But it's something that you can implement, and it's practical. And so those are some of the trade-offs. But that's why we're going to be talking about optimal tracking. And for the second homework assignment, I'm asking you to, in one of the papers, they've got an example, and it's been a while since I've looked at it, but they, in my opinion, they screwed it up. They applied a particle filter, and they could have done optimal tracking in that example, and they're like, there's no other way to do this. This is the best way, is with a particle filter, and I think I'm asking you to go through and work that example out with an optimal filter, which is really the right way to solve that particular problem. And I think you'll get a lot of insight from doing so, and I'll give you a lot of ideas about what the more advanced cases. This is just an overview of this topic. There's kind of a lot here. We'll be talking about some of the key ideas. Markov processes. I actually borrowed a diagram that I think I first saw from Dr. Wan's slides, and then we'll be going through the state recursions that are for the optimal case, which I also first saw from Eric. So, finally, here is what this class is about. We've got two equations. We've got the process model, and we've got the measurement model. There's other terms that are used for these. Sometimes this is called the observation model. Sometimes this is called the state model. But I usually call this the process model and the measurement model. The measurement model is intuitive because this is the statistical model of how you get your measurements. This is what your sensors actually produce. That's represented by the vector y. In any given time slice, you're measuring from some number of sensors, and those values are collected in this vector. And this is the statistical model of how those sensors are related to one another, and related to the state that we're trying to estimate, and related to the noise that we don't have a direct measure of. So this is usually thought of as the sensor noise. It's what the sensors do when they're not supposed to be measuring anything, when things are completely stationary and they're measuring things anyway, just due to the intrinsic noise of the sensor. This is where we put our prior knowledge, is in the design of this equation. This is where you need to use your knowledge of the dynamics of what you're trying to measure, the limitations of what you're trying to measure. If you know that your state is bounded within a certain range, if you know that it only changes in a certain way, if you know that some state variables, maybe the speed of the ship moving forward, is affected by how rapidly it is changing its heading, just as an example. All of that is represented by this equation, and this is where a lot of the engineering goes, is in designing that equation, validating it, making sure that it's right, and modeling your prior information as accurately as you can. This model, the functions f of n and h of n, everything is multivariate. All of these are vectors. You'll notice that there's a little subscript. N is the time index. All of this is done in discrete time. If you're working in continuous time, I'm assuming that you've sampled it at a constant sample rate of some sort that puts you in discrete time. So this is all designed for processing real data on a computer that's been sampled. And the discrete time index is represented by N. You'll notice that H and F, which are both can be very complicated nonlinear functions, have a little subscript on them as well. That means that the functions themselves can be time varying. So not only can the properties of your noise be time varying, certainly your state is time varying, but the relationship of your measurements to those two things can change completely from one time sample to the next. This is a highly non-stationary, time varying, as nonlinear as your imagination will go, stochastic model. And what else could you ask for? If you can come up with an optimal estimator for that case, and you're like, oh my gosh, I can do anything. Makes you feel omnipotent. And it's not quite that great. There are a few limiting assumptions, and probably the biggest limiting assumption to apply the techniques we're going to be talking about is that you know what H is and you know what F are. In some cases, you may not know what they are, and you end up doing something called system identification to try to figure out what the relationship of Y to X is, and also to try to figure out how X changes over time. But that's not what we're going to be talking about for this class, and I'll spend some time talking about it. I'm going to assume that you can either figure this out from knowledge, domain knowledge of your problem, or that you can design a reasonable model for how the state changes over time. And for this, I'm going to assume that you can figure that out by, again, knowing the properties of your problem and how what you're trying to measure is related to the things that you can actually measure, to the sensors that you actually have. So one big limiting factor, and again, it was one that tripped me up many years ago when I first took a class like this, is where do H and F come from? We'll be working through a lot of examples, but essentially the bottom line is domain knowledge and your smarts, your ability to design those two things, especially the state model. So our goal, and I'm sorry, someone noted there is a way, apparently, for me to make a better YouTube show. I can point to things on here, but it's harder for me to lecture that way. It's much easier for me to point to the screen. So for those of you watching this on YouTube, I apologize, but it's just how I do it. Our goal, once again, is to estimate the state, and we have to think carefully about what we mean by that, because estimating the state can actually mean different things. By estimating the state, we could mean we want to estimate an entire trajectory. We want to know not only where is the state right now, but where has the state been? How did we get from whatever the starting point was for the state to its current position? We're talking about tracking the position of my foot. I maybe want to know not only what's your best estimate of where the foot is right now, but what was its entire path to get there. And those, it turns out, can be very different problems. Estimating a trajectory is not the same as answering the question of what is your best estimate of where it is right now. If you approach the problem from those two different ways, you can actually end up with different answers of where the state is right now. And I'll talk more about that subsequently. Another thing that changes, now that we've got time in the picture, is that when we think about, well, what information do we have? Let's for a moment just focus on the most common problem where we're trying to estimate what is the state right now. Well, the information you have is not only what is the current measurement at time in, but we also know what the measurements have been. By time in, we will have observed all the sensor measurements from time 0 all the way up to whatever the current time is. And in many of your research problems, I know a lot of you are PhD students, and you're cranking on data that's already been recorded. And so in that case, you know not only what is the data from time 0 up until the current time, you also know what the measurements are going to be in the future as well. And if you say, well, what is the current state given the past data, you get one answer that's all right. Say, what is the state given the past data and the current data, you get a better estimate. If you say past, present, and future, you get an even better estimate. And one really beautiful thing about these state space methods is the way you get those 3 different estimates, which you may need in different situations, aren't that dissimilar. I mean, if you can do one, then you can more or less apply the same techniques to get the others. I mean, I should say that with a footnote that a recent PhD graduate, Dr. Wand, did almost a big portion of his dissertation was about how do you use future data to get a better estimate of what the state is right now for a particular type of trackers. It's not, I don't mean to trivialize it, but it all fits within the common framework that we're going to be talking about in this class. So there's a lot of power here in terms of the types of problems that you can approach, but there's also a tremendous amount of complexity. So, and you're already getting glimpses into that you're going to have to think a lot. There's a lot of concepts that are really important. So, assumptions. In this class, I'm assuming that you know what your process model is, or you can design it, which is what I usually do, and that you know what your measurement model is, this function h of n, again, or you can design something that's reasonable. And this is where there's a lot of math, and this is where there's a lot of judgment. This model is often pretty simple, but it requires really good judgment about how quickly your state is moving and what moves with what, and how quickly it can move. And this really requires that you understand how your measurements are related to what you're trying to estimate. So this comes from just really understanding that, and usually involves a fair amount of math. You also need to know what the distribution is of the 2 noises. Often the sensor noise that we have in y of n, it's often additive. So this is often some nonlinear function of the state plus additive noise. And that noise often comes from multiple independent effects. And when you've got noise coming from multiple independent effects, the central limit theorem applies, at least approximately, and your noise becomes approximately Gaussian. And so although technically you need to know the PDF of your measurement noise, usually you'll model that as Gaussian with 0 mean, and usually the variance of that noise is something you'll be able to get from measurements, by knowing what your sensors produce. In some cases you'll have measurements, you'll have sensor noise that is occasionally produces very large values, in which case a normal distribution isn't a good model, and you can use other distributions when that occurs. So there's a lot of flexibility there, but usually it's additive Gaussian noise. Similarly, with the process noise, you technically need to know what the PDF is. The most common assumption is that it's Gaussian with 0 mean, and with a variance that is the knob that you turn that controls the trade-off between the estimator using the measurements to estimate the state and using the state dynamics or your prior information to estimate the state. That's where the knob is in the variance of the process noise. We'll be going over all these concepts again. This is just the first of hopefully many times be seeing all this. I know it's a lot to absorb. And there's a lot of math in this set of slides too. Soon we'll be getting to many more examples, and there's a really nice example, I think, at the end of the set of slides too, but it takes a while to get there. All right, just a word on notation. There's a notation that I like to use that is different than the book and isn't in wide use, but was used when I first learned these techniques, and so I'm going to be using it as well. Usually the most common estimation problem is what is your best estimate of the state right now at time n, and little n always represents the current time, given all the observations. From the first observation, I'm going to arbitrarily define that as time 0. So n equals 0 is always the first observation we have, up to the observation time of n plus L. And I've made this n plus L so that if L is equal to 0, then it's past and present. If L is a positive number, that includes some number of samples into the future. And when we think about the posterior probability now, generalizing from what we covered in that first set of slides, the posterior probability that we're interested in now is that of the state at time n, given everything that we know, given all the measurements we've had. And this is a big set of numbers. It's a lot of data. It took me a while to get my head wrapped around it. This includes conditioned on what the measurement was at time 0, at time 1, all the way up to whatever the latest measurement is that you know. So it's conditioned on a lot of stuff. And that's an awkward notation. I mean, it's already awkward with the ellipsis here. But it's an awkward notation to carry, and so the notation I use is shorthand, is y sub 0 colon n. And this colon means all measurements from this time to that time, from time 0 to time n. And so when you see that used, that's what that denotes. There's another bit of notation that I use that is different than the book, and it's just what I like to use. And this is the sort of thing that's going to drive Eric crazy, but I'm going to do it anyway. There's two very common cases of how you estimate the state at time n. One is the case where you've got all the observations up to the previous time sample. We want to know the state at time n, and we've got measurements from 0 all the way up until time n minus 1. And the book denotes this as x hat of n, and then a superscript with a minus sign, where that minus sign essentially is a mnemonic, a mental reminder that this estimate was made without taking into account what the measurement is at time n. And this is often called the predicted estimate, because you're predicting one time step ahead from your current measurement. Your current measurement is at time n minus 1, and now we're estimating what the state is at time n. And so this minus means you're missing it, and that's a notation that the book and a lot of other people use. For the second, and arguably even the most common estimate, is called the filtered estimate, and it's when you have all the measurements from time 0 up to time n. And the book uses a plus to denote, a superscript plus to denote the filtered estimate. I prefer a different notation that I learned. It's just a personal preference. I like it better. I think it's cleaner. And the notation that I use is if the estimate of the state at time n, given that you've got measurements all the way up to time n plus L, I denote that as x hat of n. This tells you the time at which you're making the estimate. So we're estimating the state at time n, and we've got measurements from 0. It's always from 0, so I didn't include that here. 0 all the way up until n plus L. And so the way I would denote the predicted estimate is x hat of n given n minus 1, and the filtered estimate is x hat of n given n. So that's a notation you'll see used throughout the slides for the entire course. Any questions so far? Okay. So again, just a little bit on notation. If we've got y of 0 to L, and we're estimating x at time n, if the lag is 0, so we've got all the measurements, it's called the filtered estimate. If we've got up till the previous time sample, it's called the predicted estimate, one-step predicted estimate. And if L is greater than 0, and so we've got future measurements as well as the current measurement, then it's called a smoothed estimate of the state. And there's several different flavors of smoothed estimates that we'll talk about later this term if we have time. And one of our goals, one of the things that's intimidating about this, we were just thinking about this, and it's 1960, and there is no common filter, and no one's figured out how to generate these estimates. So you're sitting back and you're thinking about this, you're thinking, oh my gosh, the last thing in the world I want to do is think about how to estimate the state at time n, given the measurements from 0 to, let's just say, up to time n, because that estimate could be affected by what the measurement was at time 0. And so this estimation problem is getting harder and harder as time goes on. I've got more and more measurements, more and more data that I've got to take account of as time goes on. And thinking about implementing this in real time with an algorithm that's running on a processor where the amount of computation required to generate each estimate grows with time, you're not going to be able to do it. I mean, you're very quickly going to run out of cycles, it would seem. And one thing that's common to basically all of the state space tracking algorithms, and the reason that maybe this is an engineering course and not a math course, is that we're not trying to solve the mathematical problem, we're trying to solve practical problems where we actually have to implement this. And so what we want is an efficient recursion. where the amount of computation required does not scale with time. Even though it's taken account of a larger and larger set of measurements, the computation at time in is no more than it is at time in plus 1, or than it was at time in minus 1. So we want the computation to not scale with time. That's really important if we're actually going to be able to implement this on practical problems and not have it just completely bog down the processor after a few samples or a few seconds. And that'll be true of all the algorithms, even the optimal tracking algorithms that we're going to talk about in this set of slides. So once you have the posterior distribution, there's, as we talked about in the first lecture, there's many estimates of the state that you could use. The vast majority of the literature is about estimating the mean that minimizes the Bayesian mean squared error. That's what everybody talks about. That's what the Kalman filter is for, the unscented, the extended. You can go through the list. They're all about estimating the mean of the distribution. But it's not the only one. And if you've got a multimodal distribution, which you often have, it may not even be a reasonable estimate for the reasons we talked about in that first lecture. And there's other things you can think about. You say, well, give me the one that maximizes the posterior distribution, which is the so-called map estimator. We'll talk about a really beautiful way of doing that partway through the term. You could also think about doing a median estimate, which is robust to heavy-tailed distributions. So there's other things that you can use. And I encourage you to think about this, because with particle filters, although we have a way of calculating this, we've got an approximation of the posterior distribution itself with particle filters, and you're no longer limited to only calculating the mean. You can do it, but there's other things that you can think about and should think about when you're working with particle filters, and especially nonlinear, highly nonlinear dynamics that can generate multimodal posteriors. And one of the other things that will come out of this sort of part of the teaser on Monday, is that we'll also be able to obtain confidence intervals and a measure of covariance of our estimates, which is outstanding. That's just icing on the cake that you usually don't get in most algorithms. So when we think about optimal recursions, an optimal algorithm for doing tracking, let's just consider the filtering problem for now. And by the filtering problem, what I mean is estimating the state right now, given all of the past and the current measurements. So taking the measurements from time 0 all the way up to right now, and we want to estimate what is the state right now. That's the filtering problem. It's not prediction, it's not smoothing, it's what are things right now. There's two PDFs that you might think about, that you should think about. And one is where I'm going to call the joint PDF, and the other is the marginal PDF. Now by joint PDF, I have to be careful, because this joint PDF is also a conditional PDF. It's still the posterior PDF in that we're looking at the probability of a state trajectory given all the measurements from 0 all the way up to the current time. But this is a joint PDF because it's talking about, or it's looking at the entire trajectory, the entire state trajectory from time 0 to time n. This is a high-dimensional thing. The dimension of this grows with time. If the dimension of the state vector is represented by m, then the dimension of this distribution, there's n plus 1 samples, and each state has m dimensions to it. So the dimension of this is huge. And this is mapped onto a PDF which only produces one value, but still, this is a very high-dimensional thing. The dimensionality of this grows with time. But if the question that you want to answer is not what is the state right now, but what was the trajectory? What was the most probable trajectory? What's the mean trajectory? If you care about the trajectory, the state trajectory, then this is really what you should be thinking about. If you only care about give me your best estimate of the state right now, then what you care about is what I'm going to call the marginal PDF. It's a marginal because if you integrate out all of the state variables from 0 to n minus 1, then you get this. So it's a marginal distribution of this joint distribution. And it is the PDF of the state at time n, given all the measurements from 0 to time n. Just two different cases.
What is m again?
M is the dimension of x.
Dimension of x.
at any given time. It's the number, how big is your state vector? How many state variables do you have? That's what M denotes. I'm sorry, I didn't define that earlier, but that's what that is. Any other questions so far? Okay, so for doing the optimal recursions, it turns out there's an optimal set of recursions for both of these. And so we'll go through each of them. There's two that we're going to get out of this set, although it's first. Before we go through that recursion, there's another key idea that you need to be aware of that is implicit in these two equations. And that is that we're assuming that the processes we're working with are what are called a Markov process. And what that means, essentially, is that the PDF of the measurement conditioned on the state trajectory, the entire state trajectory, is the same as the PDF of the measurement conditioned on just what the state is right now. What that means is all the information in this entire trajectory of states, all that entire history is represented in what the state is right now. And that the measurements that you take right now only depend on what the state of the system is right now. It's the Markov assumption, and it's key to everything that we do. So if you know what the state is right now, you don't get any additional information by knowing what the previous values are of the state. And this also applies for the process model. So along with that is an assumption that the state at time n plus 1, conditioned on all the entire trajectory of the state, is the same as the PDF of the state at time n plus 1, conditioned only on what the state was at the previous time sample. So it's the same idea that the entire memory of the process is represented by whatever the current state of the system is.
The distribution is memory less.
I think that's right. It's a memoryless distribution, is that right?
Yeah, that sounds
Yeah,
like.
that sounds right. Yes. Probably learned about that in signals and noise. This is the diagram that I ripped off of Eric Wan long ago. So here you can see this is a model of how things evolve in time. So we've got the state here at time n minus 1. We've got noise at time n minus 1. And you combine those two, and it generates what the measurement is at time n minus 1. The key thing here is that y at n minus 1 is only affected by the previous values of the state through x at n minus 1. It is the bottleneck. It contains all the information about the past that you need to know in order to generate the current measurement. And likewise, it contains all the information you need to know to characterize what the state is going to be, well, that and the noise that gets added in. But there's nothing, I don't know if that would be upstream or downstream, I guess upstream of x of n minus 1 that you need to know or that would affect x of n. So as you go through time, the entire memory, part of the memory, the previous trajectory that you care about, is completely represented by what the state is, by that state vector. That's the, I guess, memoryless property or the Markov property. And that's a key assumption for what we're doing. And it doesn't always apply. There are some processes that have a longer memory and are not affected, where you can't get just a single state variable like that that completely represents the past. A pure delay is a good example of that. If your system is that y is equal to what the state was long ago, then in the simple case that would be violated, although there is a way of incorporating memory into the state, and so you could still represent that as a state process, but I guess that's not a good example. Well, this can be used in many applications, so you shouldn't blame me if I have a hard time thinking of an example where this wouldn't work. Okay. So let me take you through this, and then we'll do this. We'll go through this set of recursions one more time on Monday next week. So Bayes' theorem. Joint probability is equal to the product of the conditional and the marginal. And you can do that either way. You can say this is x conditioned on y times the probability of y, or you can do the probability of y conditioned on x times the probability of x. It would be almost like a commutative property. In our context, it's more complicated. We've got trajectories that we've got to worry about. And for reasons, it drives me crazy as a student when I see something like this, because I see that equation on a slide and I think, where on earth did that come from? You say, in our context, this becomes, and then you come up with this crazy distribution. I have no idea where it came from. And the answer is, well, this came from knowing what result I wanted, and this is a way of mathematically representing that. So I wouldn't expect you to know to come up with this, but that's what I'm going to work with. So if we've got the entire state trajectory and the measurement at time n, we've got this joint probability conditioned on all the previous measurements from time 0 to time n minus 1. And we apply Bayes' theorem in just the right way, and I wouldn't expect you to think of this as the right way, but if we apply this in just the right way and split this out two different ways. So one way is we take the y of n and we condition on it, and then we multiply that times the marginal, the probability of y of n given its entire past values of y of n. This is one way to split it out, and we can simplify this a little bit with our notation, because 0 to n minus 1 and y of n, that entire set can be represented as just y of 0 to n. So from this step to this step is just really a notational simplification. And so this is the posterior distribution that we're interested in. And now we've got one way of relating it to this joint distribution. The joint distribution is equal to the thing we're interested in times this. So that's one way to split it out. Just like we can split this out two different ways, if we choose differently and split this out a different way, we can get another equality of what that's equal to. And that looks like this. This is really odd. I think that projector isn't working quite right. Some of these are actually colored blue, but the entire set of text looks blue.
That's what
on
I
the
was
screen.
saying before. It's bluish.
Yeah, it's okay. So it's missing colors, or some colors are faded. All right. Well, anyways, I'll walk you through this. So this is the same starting point that we had on the previous slide, same joint distribution. And now, instead of splitting out the way I did before, now I'm going to move this to the right and condition on x of 0 to n, and move that to the right. So now this is over here. And on this side, we've now got the marginal, the probability of x of 0 to n, given the past values of y of 0 to n minus 1, previous measurements, past measurements. Here's the first time we use that Markov property. We said if we've got a Markov process, then the distribution of y of n, given the entire trajectory of state variables, and adding the past values of y doesn't add any additional information because that also depends on the past state variables, then this whole thing is just equal to the probability of y right now given what the state is right now. If we know what the state is right now, then we've got the PDF of y then. We don't need anything else. So we get a big simplification going from here to here because of that Markov property. And then another trick, if we represent this a little bit differently, I'm going to split out. This is just a notational change. So I'm going to represent this as x of n, and then the entire past of x of n, the past trajectory. And then I condition on that using this Bayesian technique again. Now I've got the probability of x of n given the entire past trajectory, the entire past set of measurements, times, and then we've got the marginal, which is a probability of x of 0 to n minus 1 and 0 to n minus 1. Now, there's a couple of things to note about this. One is this popped up, which is a good thing. That is the that's the posterior at the previous time sample. That's one of the things that we wanted for the recursion, and it just showed up. That's a really good thing. The other is that now we can use the Markov property again. We've got x of n conditioned on a whole bunch of things. But if we know what the state is at time n minus 1, if that's one of the things we're conditioning on, then all those other things fall away because of that Markov property. If we know what x of n minus 1 is, then there's no additional information gained by knowing previous values of the state or previous values of the measurement. And so this also becomes much simpler. And now, if we take this and the results on the previous slide, we very rapidly end up with something beautiful. This is the equation that was on the previous slide. This is what we were trying to estimate. And both this and this are equal to the same thing. They're both equal to this thing that I contrived to get to this equality. And so what we end up with is the beautiful recursion, the Bayesian posterior trajectory. And it's beautiful. It's very tidy, it's intuitive. You know, we've got the posterior of the trajectory at time n is equal to what it was at the previous time sample, and then multiplied by a few different things. This doesn't depend on x, so it's going to turn out to not be of much consequence. If we want to just estimate x, we really don't need that. And this we can get from our measurement model. I'll show you how next week. And this we can get from our process model. I'll show you how next week. So it's great, right? I mean, what else do you need to do? Well, the problem is, despite the beauty of this solution, is that you can't actually use it. This isn't practical, even though it's beautiful mathematically. And the big problem is that we're talking about trying to handle something that is growing with time. We're talking about a joint distribution. And if you look at the argument of this, we've got an m dimension, m times n plus 1 argument for x here. And if you want to estimate the mean, what are you going to do? An integral over m times m plus 1 dimensions? You can't. It's not computationally viable. I don't even know how you would represent this. You know, if you're talking about a general PDF, you can't represent it by a mean and a variance. It's not like a Gaussian distribution. We're not making an assumption that anything is Gaussian. This almost never is Gaussian. So how do you represent that? You don't have a finite set of parameters that you can use to represent this. And it's changing over time. It's growing with time. So it's too big to handle. It's almost like too big to fail. You can't deal with it. And we also have a problem that if you did care about this, that can't be computed analytically either, although that's of much less consequence. So although this is beautiful, it's really somewhat useless at the end of the day, except in very limited cases. The only case where this does suddenly become tractable is in the case where everything is linear and Gaussian. And when you do that, you end up with Kalman filter recursions that we'll talk about towards the end of this term. And that's nice, that's cute, but we're interested, I think, especially for the first part of this class, in the nonlinear case. And so this, you know, it's a beautiful theoretical result that you can't use as an engineer. The mathematicians love it, the engineers think it's useless. That's kind of where we end up. So I'll go over this again briefly on Monday, because I know a lot of you probably, your attention has to have waned by this time, and we'll stop there today. And someone will have their name drawn out of the hat on Monday, so make sure you get your homework submitted and be prepared to go over it. Thanks.